Now, Laplace transform can be used to solve ordinary differential equations. Well, so moreover, until now, the way we usually solve differential equations, we first found a general solution of the homogeneous equation, of the differential equation, and then we used the initial values to find the values of the constants and it gave us a specific solution of the initial value problem. So the Laplace transform can also be used to solve differential equations, but Laplace transform is used to kind of solve the whole thing at once. Although, to be honest, I think Laplace transform, solving differential equations using the Laplace transform usually requires more effort than solving them directly using the characteristic equation like we did before. But anyway, let me explain. It is still Laplace transform is still a very, very useful trick, and it is worth learning about the Laplace transform, because not only it appears in the theory of differential equations, the theory of differential equations is actually probably maybe one of the least important applications of the Laplace transform. So it is used in image processing and in a lot of areas, really. So anyway, so in order to do this, we are going to use the following properties, right? So we are going to denote, so let the Laplace transform of the unknown function y to be y capital, all right? So that's a y capital of s. Then by the property that we just saw, the Laplace transform of the derivative is sy minus y of 0, and y of 0 is 3, so plus 3. And then L of y double prime is s square y minus s times y of 0, and y of 0 is 3, so it is going to be plus 3s, and then minus y prime of 0, and y prime of 0 is 1. Okay. So another thing that we need is the following property. Well, I mean, we actually saw this, so that the Laplace transform of an exponential function e to the minus at is 1 over s plus a. Okay, so now what we are going to do, we are going to apply the Laplace transform to the right hand side of this differential equation, right? So then how does it work? The Laplace transform of the second derivative is s square y plus 3s minus 1, so this is the Laplace transform of y double prime. So then plus y prime, the Laplace transform of y prime is sy plus 3, so this is the Laplace transform of y prime, and minus 2y, yeah, so this is the Laplace transform of minus 2y, should be equal to 0. When I did that, I have used the fact that the Laplace transform is a linear transformation of vector spaces. Okay, so let me group together all the terms with y. So s square plus s minus 2 y, and then all the terms without y, I'm going to move them to the right hand side. So I have 3s here, so it becomes minus 3s, and plus 3 becomes minus 1 plus 3 is plus 2, so minus 2. Then solving for y, I'm going to get y equals minus 3s plus 2 divided by s square plus s minus 2. So in other words, what I have found is the Laplace transform of the solution of this initial value problem. So now, how do I find the solution of the initial value problem itself? So in order to do this, I need to express this as a sum of partial fractions. Now, I'm not going to explain how to do partial fractions again, because you must have learned it in secondary school, I guess, or in foundations of mathematics, or, well, you must have learned it before. If you don't know how to do it, I suggest that you just watch Hans Academy. So they have excellent videos about partial fractions. So expressing this as a sum of partial fractions, I'm going to get minus 4 over 3s plus 2 minus 5 over 3 times s minus 1. Well, but notice that this is minus 4/3 times the 1 over s plus 2 is actually the Laplace transform of e to the minus 2t. Right? And this is minus 5 over 3, and 1 over s minus 1 is the Laplace transform of e to the t. So, which means that the answer is minus 4/3 e to the minus 2t minus 5/3 e to the t, which of course you can verify very easily, or just try to solve the same initial value problem in Wolfram alpha. You will see that it is the correct answer. So here is again the summary of what's going on.